All right, so let's look at the solutions for our quiz review for 3.1 to 3.5. Please remember that all of these terms mean the exact same thing. Slope of the tangent line, instantaneous velocity, instantaneous rate of change, marginal, derivative, f prime x. So they could ask any of these questions in that way and it would mean to do the same thing. All right, so for this first one, we have two things that are being multiplied. So two ways we can do that. You can either go through and multiply everything out first and then take the derivative with power rule, or you can do the product rule, either one. So over here, if we go through and multiply, we're going to say x squared times x squared is x to the fourth. X squared times 3x is 3x cubed. X squared times negative 4 is negative 4x squared. 5 times x squared. 5 times 3x, 15x, and 5 times negative 4 is negative 20. We could combine like terms here to give us a positive 1x squared. So we haven't taken the derivative yet. All we've done is just simplify. So now we're ready to take the derivative. So the derivative of x to the fourth is going to be 4x to the third. Derivative of 3x cubed is 9x squared. Derivative of x squared is 2x to the 1, or 2x. Derivative of 15x is 15 times 1, or 15. And the derivative of negative 20 is 0 because the derivative of a constant is 0. The other way we could do that is with our product rule. So for product rule, we're going to do first. So here's first and here's second. So we're going to do first times derivative of the second. So the derivative here would be 2x plus 3 plus 0. So first times derivative of second plus second times derivative of first. The derivative of this guy would be 2x. All right. And now I'm going to need to FOIL here. So x squared times 2x is 2x cubed. X squared times 3 is 3x squared. 5 times 2x is 10x. 5 times 3 is 15. And then over here, distribute. 2x times x squared is 2x cubed. 2x times 3x is 6x squared. And 2x times negative 4 is negative 8x. So combining like terms, 2x cubed and 2x cubed is 4x cubed. And then 3x squared and 6x squared is 9x squared. 10x minus 8x is 2x, and then plus 15. All right, for number 2, same idea. They want us to find the derivative. This one we have a quotient, so we're going to do denominator, x squared plus 1, times derivative of numerator, so derivative of x squared is 2x, minus numerator, x squared, times derivative of the denominator, so the derivative of x squared plus 1 would be 2x. So denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. Okay, so here we'll distribute. So x squared times 2x would be 2x cubed, and 1 times 2x would be 2x, and then x squared times 2x is 2x cubed. So the 2x cubed and the negative 2x cubed canceled each other out, and that left us with just 2x. And then down here in our denominator, we've got that denominator squared. Now, if you want to multiply that out, you can, but you don't have to. And remember, you can't do something like cancel this x with this x, because you can't cancel things that are being added and subtracted to something else. All right, then for number 3, they asked us to find the equation of the tangent line for number 2 at x is equal to 1. Okay, so just a second ago, this is what we got for our derivative, or our slope of the tangent, and we want to find that at 1. So that just means I'm going to put in a 1 for x right here, and I'm going to put in a 1 for x right here. So that would give me 2 times 1 in the top, and 1 squared plus 1, or 2 squared in the bottom. So that's where we're getting the 2 times 1 in the top, and the 1 plus 1, or 2 squared in the bottom. So our slope is 1/2. So now we have a point and a slope. All right, where do we get the point? Because they only gave us x equals 1. Well, if we know x is equal to 1 and we want to find y, we just plug 1 in, right? So 1 squared over 1 squared plus 1 is where we are getting our y value of 1/2. Okay, so here's our ordered pair, 1, 1/2. And then here's our slope, 1/2. So I'm going to do y minus y1 is equal to m times x minus x1. And so I can distribute my 1/2, so that'd be 1/2 x minus 1/2. If I add 1/2 to both sides, then that would give me slope-intercept form. And if it's supposed to be in standard form, I got to move everything over to one side, set equal to 0, and get rid of the fractions, because remember that the coefficients of x and y cannot have any fractions in them. So I'm going to multiply that whole thing by 2 or by -2, either one, and that would give me my equation in standard form. All right, then for number 4, they gave us the graph of the original, and they asked us to graph the derivative. So step number 1, look for horizontal tangent lines. So I have a horizontal tangent line right here, and right here. Those will be x-intercepts on my derivative. So sure enough, you can see x-intercept, x-intercept, x-intercept. All right, then we're looking for where the original function is increasing, it's positive, and where the original function is decreasing, the derivative is negative. So we know that we have an x-intercept here, and we know that it changed from increasing to decreasing. So that means it's going to change from positive to negative. We also know that we have an x-intercept here, and it changed from decreasing to increasing. So that means it's changing the derivative from negative to positive. Then I know that I have an x-intercept here, and I know that it changes from increasing to decreasing. So it should change from positive to negative. Then if I'm still unsure, like, right now I've got this piece right here, and I've got this piece right here, and I've got this piece right here, but I don't really know how low down to go, and I don't really know how high up to go. So that's where those strategic points could come into play, where, kind of halfway between the two x-intercepts, if I want to draw a slope, you can see that's about a -1. So halfway between those two x-intercepts, I would be down here at -1. And then similarly over here, halfway in between my two x-intercepts, I could plot a strategic point. So maybe about right here looks like a slope of about a +1. And so I could come over here halfway between the two x-intercepts and plot a +1. So that would be the graph of my derivative given the original. All right, for number 5, they ask us where and why the function is not differentiable. There are 3 things that we're looking for on this graph. First, we're looking for any discontinuities. Anywhere I have to pick up my pencil. So I'm going along, and right here at +1, I have to pick up my pencil. It's discontinuous because the limit doesn't exist. And then also over here at 7, I have to pick up my pencil, because even though the limit exists and the function is defined, the limit doesn't equal the function. Now, you do not have to be that specific. All you have to do is just say there's a discontinuity. Okay, so that's the first thing we're looking for, is it discontinuous? The second thing we're looking for is a corner or a kink in the graph. And so you can see a corner right here. And the reason for that is always going to be the derivative from the left doesn't equal the derivative from the right. Because you can see right here, derivative or slope would be positive here, and slope would be negative here. So the derivative from the left doesn't equal the derivative from the right at 3. And then the last thing we need to look for is a vertical tangent, meaning if I drew a tangent line, it would be a perfectly vertical line, and the slope of a vertical line is undefined, and slope of tangent is derivative, so derivative would be undefined. And so right here at 6, we have a vertical tangent line. All right, then for number 6, we want to know all about particle motion. All right, so to begin with, here's our original equation, and they ask us to find the velocity. Now remember, velocity is the first derivative. So I'm going to go through and take my derivative here. So 3 times 2/3 would give me 2t. Reduce this by 1, so 2t to the second. And then 2 times 5/2 would give me 5t. Reduce this by 1, that'd be 5t to the first. Derivative of 3t, remember the derivative of t or x or whatever that might be is just 1. So that would be 3. And then the derivative of a constant is 0. All right, then acceleration is the second derivative. So the derivative here is going to be 4t minus 5 plus 0, so 4t minus 5. And jerk is the third derivative. So the derivative of 4t is 4, and the derivative of -5 is 0, so that would just give us 4. Then they ask us where the particle is at rest and where we have horizontal tangent lines. Those are actually identical questions, because the particle is at rest when its velocity is equal to 0, and we have a horizontal tangent line anywhere the slope of the tangent line is equal to 0. since velocity is derivative and slope of the tangent line is derivative, we're doing the exact same thing on both of these. We are setting the derivative equal to 0 and solving. Okay, so here's our first derivative, velocity. We're going to set that equal to 0 and solve. That's a quadratic, so you could solve it by factoring, completing the square, or quadratic formula. This one factors pretty easily, so I'm going to factor it and set each of my factors equal to 0. So if t minus 1 equals 0, add 1 to both sides, t equals 1. And if 2t minus 3 is equal to 0, add 3 to both sides, divide by 2, and t is equal to 3/2. All right. If we want to know where we have horizontal tangent lines, again, that's going to be where the slope of the tangent line is equal to 0, so where the derivative equals 0. So I would have done the same thing. I would have found the derivative, set it equal to 0, and solved. So you can see I'm going to get the exact same answers there. All right, then for F, we want to know where the particle is moving forward and backward. And it's moving forward anywhere velocity is positive, and it's moving backwards anywhere velocity is negative. So let's make a sign graph for velocity. All right, we already set the velocity equal to 0 and found out we have x-intercepts at 3/2 and 1. So here's 1, and here's 1.5 or 3/2 right here. So to make my sign graph, I'm going to pick a test point. So I'm going to pick perhaps 1/2 or 0, something like that to plug in. All right, so let's say that I plug in 0. I'm going to get 0 minus 0 plus 3. So I got a positive value right here. Cross a single root, the sign changes to negative. Cross a single root, the sign changes to positive. Now, if you preferred, you could test every one of those intervals. So you could come in here and you could plot like 1 1/4, put that into your equation, and you could put something like 2 into your equation. And again, you're going to find out that this interval is negative and that this interval is positive. So I don't actually have to graph this. All I have to do is make my sign chart to know where my graph is positive and negative. So again, moving forward, anywhere that it was positive. So from 0 to 1, it was moving forward because it was positive. And from 3/2 on to infinity. All right, then this little piece in here was from 1 to 1.5 or 1 to 3/2. That's where it was negative, so that's where it was moving backwards. Because this was a particle and they told us that time was positive, that's why we started at 0 instead of negative infinity. All right, then we want to know where the particle is speeding up and slowing down. So it's going to be speeding up wherever velocity and acceleration have the same sign. It's going to be slowing down wherever velocity and acceleration have different signs. So we've already got the sign graph for velocity, so let's just copy it down here. So that's that exact same thing we just had. And now let's make a sign graph for acceleration. So acceleration was 4t minus 5. So let's set 4t minus 5 equal to 0 to get our roots. And so we'll add 5 and divide by 4. So the only root is going to be right here at 5/4, or 1 1/4. All right, so I'm going to pick a test point and plug in. Now, if I'm trying to figure out where acceleration is positive or negative, when I pick that test point of, say, +1, I'm plugging it into acceleration, because I want to know if acceleration is positive or negative. All right, so if I take 1 and I plug it in, you can see I'm going to get 4 minus 5. I'm going to get a -1. So that means that I'm negative over here. Cross a single root and the sign changes. Or again, if you would prefer to plug in a value over here, like maybe you plug in +2, 4 times 2 is 8 minus 5 is a +3. So again, you can see it's positive over here. So if you'll notice, from negative infinity to 1, the signs are opposite. This is positive, this is negative. So from negative infinity to 1, and because they told us time is greater than 0, for us it would be from 0 to 1. It's slowing down because the signs are opposite. All right, then from 1 to 1.25, this is negative and this is negative. So from 1 to 1.25, the signs are the same. It would be speeding up. At 1.25, this changes to positive. So from 1.25 to 1.5, accelerate